Nagbabalik po ang DepEd Hour para sa Tele Turuan. Ito ay alalay ng tanggapang pansangay sa iba't ibang alternative delivery modes na ginagawa ngayon sa mga pampublikong paaralan.
Tumutok lamang po sa pakikinig at panonood upang matuto sa ating Tele Turuan.
Good day to our dear televiewers and subscribers. Welcome to DepEd Tele Turuan. I am Mary Ann C. Ramitere, Junior High School Teacher 3 of Campiño National High School, your teacher presenter in Mathematics 10. Today, we will be discussing the lessons in Module 1 for the second quarter entitled Illustrations and Graphs of Polynomial Functions. Before we proceed with the lesson's learning objective, you may look at your Module 1 for Quarter 2 entitled Illustrations and Graphs of Polynomial Functions, since what we are going to discuss today is in line with the said module. In addition, this module was written by Sir Genaro P. Matamis of Mayapiap National High School. And these are our learning objectives. Number 1, illustrate polynomial functions. And number 2, describe and interpret the graphs of polynomial functions. Did you know that polynomial functions can be illustrated by an equation derived from a piece of rectangular cardboard? Yes, that is true. We can make polynomial functions by making an open box. How are open boxes made? Number 1, take a rectangular cardboard. Number 2, cut each corner by following the dotted lines. Number 3, fold along the thin lines. And number 4, staple or glue the sides to each other. We now have an open box. Now consider this rectangular cardboard. Its length is 30 units and its width is 20 units. From this cardboard, we will make an open box by cutting an X unit. The cut made will become the height of the open box. Its length and width will become 30 minus 2x and 20 minus 2x respectively. Since the volume of the box is represented by this formula, so the volume of the open box is V of x is equal to x multiplied by quantity 30 minus 2x multiplied by quantity 20 minus 2x. This equation is now an illustration of a polynomial function. Now let us define polynomial function. A polynomial function is a function defined by this equation, where n is a non-negative integer and the coefficients a sub n minus 1, a sub n minus 2 until a sub 1 and a sub 0 are real numbers, and a sub n is not equal to 0. This polynomial function p of x may start with function of x or f of x. It can also start with y. In addition, a sub n is the leading coefficient, and n is the degree of the polynomial. Take note that a polynomial function has no variable in the denominator, has no variable with a negative exponent, has no variable under a radical sign, has no variable with fractional exponent. Now let us identify which among the items below are polynomial functions. Number 1, f of x equals 2 minus x plus 3x squared minus 4x raised to 4. Yes, it is a polynomial function. Number 2, g of x is equal to 3x squared minus 4x plus 1 minus x raised to negative 1. It is not a polynomial function, since it has a variable with a negative exponent. Number 3, g of x equals 2 over x plus 1. It is not a polynomial function because it has a variable in the denominator. Number 4, f of x equals the square root of 7x plus 3. It is not a polynomial function because it has a variable under a radical sign. Number 5, g of x equals negative 4x squared plus 2x raised to 3 over 2 plus x. It is not a polynomial function because it has a variable with fractional exponent. Number 6, h of x equals the square root of 5 multiplied by x raised to 7 plus 2x cubed minus x. Yes, it is a polynomial function. Now let us proceed to the steps in graphing polynomial functions. Step 1. Find the x-intercepts. Step 2. Find the y-intercept. Step 3. Use leading coefficient test to check the graphs and behavior. Step 4. Apply multiplicity of a0 of a polynomial function. Step 5. Check the turning points. To find the x-intercepts, we have to factor the polynomial completely. Then, let y be equal to 0. Finally, apply zero product property to solve for x. To find the y-intercept, we have to let x be equal to 0 and simplify. There are 4 cases in using the leading coefficients to check the graphs and behavior. Here's the first case. If the leading coefficient a sub n is positive and the degree n is odd, the graph rises on right and falls on left. Second case. If the leading coefficient a sub n is negative and the degree n is odd, the graph rises on left and falls on right. Third case. If the leading coefficient a sub n is positive and the degree n is even, the graph rises on both left and right. Fourth case. If the leading coefficient a sub n is negative and the degree n is even, the graph falls on both left and right. To apply multiplicity of a0 of a polynomial function, consider these conditions. If it is an even multiplicity, the graph crosses at each x-intercept. If it is an odd multiplicity, the graph touches or is tangent to the x-axis at each x-intercept. If it is expressed into quantity x minus r raised to k, and k is greater than 1, then the graph flattens out at the x-intercept. To check the turning points, use this formula. The number of turning points is at most n minus 1. Consider this first example. Y is equal to quantity x plus 2 multiplied by quantity x minus 1 cubed. Again, the first step is to find the x-intercepts. Since it is already in factored form, we can now let x be equal to 0. Then apply zero product property to solve for x. Get the first factor and equate it to 0. Solving for the value of x, we have x equals negative 2. Get the second factor and equate it to 0. Solving for the value of x, we have x equals negative 1. So, the x-intercepts are negative 2 and 1. Step 2 is to find the y-intercept by letting x be equal to 0. Then, 0 plus 2 is 2 and 0 minus 1 is negative 1. Negative 1 cubed is negative 1 and 2 times negative 1 is negative 2. So, the y-intercept is negative 2. Step 3 is the end behavior of the graph. Let us get the leading term by multiplying x by x raised to 3. And this is equal to x raised to 4. We can now see that the leading coefficient is positive and the degree is even. So, this is case number 3. Therefore, the graph rises on both left and right. Step 4 is the multiplicity of a0 of a polynomial function. At x-intercept negative 2, it has an odd multiplicity. So the graph crosses at x equals negative 2. Then continue to cross at the y-intercept. At x-intercept 1, it has an odd multiplicity. And since 3 is greater than 1, so the graph crosses and flattens at x equals 1. Step 5 is checking its turning point. Since its degree is 4 and 4 minus 1 is 3, therefore it has at most 3 turning points. In our graph, it has 1 turning point. So we got it right. This is now the graph of the given polynomial function. Take note that if we want to accurately graph a polynomial function, we may consider finding the other points in between the x-intercepts. There you have it. Please stay tuned for more discussion on our lesson. We'll be right back.